welcome Professor Manas Paliwal, my colleague in Material Science and Engineering Department. Professor Paliwal is a PhD and postdoc from McGill University, Canada, and Professor Paliwal is a significant contributor to the CalFET-based computational materials design software called FactSage. And what we are going to see today is what are the capabilities of this branch of computational materials design and how we can use the software to solve some of the trivial and some of the non-trivial problems in material science field. We'll be talking about, I think, precipitation, homogenization, and many other aspects of material processing. So, without any further delay, let's welcome Professor Paliwal.
Thank you. I should be audible, I guess, now. Thank you. So, as Amit introduced, so I've been associated with FactSage for more than 11, somewhere around 11 years now. And in this talk or in this presentation or in this lecture, what I have planned is that I have organized some case studies, all right, some real case studies where we have applied FactSage to understand some of the process parameters, and I have given some case studies that are practiced in plants. Okay, so in the second half, what I usually do is I take problems from the audience. So you can, depending on your system and depending on your process, we can try to understand with help of FactSage whether we can understand or improve your process parameters and things like that. All right. So first 1 hour, I'll just introduce about FactSage, the kind of problems, a little bit of physics behind the software, and then we'll quickly jump on to case studies. And once you are familiar with the capacities or the functionalities of the model, you can shoot any questions or shoot any problems that you are interested in. I initially thought that most of my audience would be aluminum alloys. Then I was informed that no, there are some people working in titanium and nickel as well. So my case studies are mostly in aluminum, but we can of course do calculations related to titanium and nickel and both ferrous and non-ferrous systems that you might be interested in. Okay, so the primary backbone of any computational software is the database, because it's a database which eventually decide the accuracy of your calculations, right? And the primary light alloy database, which includes aluminum, magnesium, nickel to an extent, is called FT-Lite database here. And this database development is going around for almost 18 years now. So we have been working on the FT-Lite database development for a very long time now. It's a big team, as you can see. Primarily École Polytechnique, which is in Montreal. So this is the developer of the software. At McGill, we had a big team as well. Similarly in Concordia. And now, since I have moved back to India, I have been contributing to FT-Lite database as well. This database development was supported extensively by industries. So these are some of the industrial mentions here. And what you can see here, this is the capacity or the solutes or the elements that this database can handle. So as you can see, these are your this is very extensive in nature. Almost entire periodic table is here, but this can actually cater to almost all aluminum alloy series. The one in red, of course, is aluminum, which is your principal alloying element. The one in blue are your second principal alloying elements. So you have copper, iron, magnesium, manganese. The one in green are your third principal elements, if you can call them. So the interactions of all these elements are taken care of. The one in underlined are still under development. So these interactions are still being incorporated in the database, but it's an extensive database, and most of the elements are covered. A little bit about CalFAD approach that is followed for the database development. CalFAD, I'm not sure how many people are aware of this technique, but CalFAD stands for calculation of phase diagram. So this is what it means. So what we do is we collect phase diagram data from literature. I'm sure everyone knows what a phase diagram is, I believe. So it's nothing but a solid liquid gas phase equilibrium representation. And we also collect some thermodynamic property data, all your extensive properties such as heat capacity, activity, enthalpy of mixing, that is collected from literature. And the idea is to have Gibbs energy as a function of temperature, composition, and pressure of all the phases in the system. Okay, so this is what we strive to do, and we try to select an appropriate thermodynamic model which has a high predictive ability, right? And then once we can develop mathematical models for the Gibbs energy of the phases that we are interested in, we can go about construction of databases. We start from a very single unary system, then we move on to binary, then we have some extrapolation functions that take care of ternary and multi-component system, right? And then you can use, so once you have the databases, you can either use FactSage. Is anyone using thermocalc? Yes, so either you can also use thermocalc or Panda to apply these thermodynamic databases to your own calculations, right? You can do any kind of complex chemical reactions. We do solidification and equilibrium calculations. I'll show some examples related to it. You can do any kind of phase diagrams, right? Any quasi-binary, ternary. I'll show you some examples with this phase diagram calculation. And some more advanced use is to do process simulation. All right, so this is something that we are doing very currently. So this is the idea of what a CalFAD approach is. Just to give you a more idea, so this is fundamental thermodynamic function that I teach in my second year class. So this is the Gibbs energy function as a function of enthalpy and entropy. This is for a pure compound. You can expand enthalpy as a function of H298 and Cp. Similarly, you can expand entropy as a function of S298 and Cp as well. So the database actually contains H298, Cp, and S298 function, right? I mean, if you can store for any given compound these information in a database very systematically, you can go about constructing a multi-component database, all right? So this is for pure component. For solution, we use what we call solution models, right? So this is the Gibbs energy function for a very simple regular solution model, right? I mean, if you recall your undergraduate thermodynamics, this is the most simpler or the simplest form of Gibbs energy expression for a solid or a liquid solution, right? So this is your pure term, this is your entropy term, and this is your excess Gibbs energy, right? So what we do is we express the excess Gibbs energy function, Gibbs energy as a function of composition, right? So QAB becomes the model parameter. So in the databases, you actually go on storing your QAB, all right? So you can systematically do it for the binaries, and if you have some information for your ternary, you can also optimize your GXs, all right? So this is a very simple example, but in reality, when we go about doing database development, we use more complex thermodynamic models. so that they are more predictive and they describe the structure of the solution, all right? But this is the overall idea. So this is about database development. And now once, as I said, once you have the databases ready, you can do Gibbs energy minimization, right? Faxage, thermocalc, Panda, they all minimize your Gibbs energy to calculate equilibrium, right? Once you minimize Gibbs energy, you can do n number of calculations which include any phase diagram section, right? So for instance, this is magnesium, aluminum, cerium, manganese, yttrium, and zinc alloy. This is a multi-component magnesium alloy. I am fixing cerium, manganese, yttrium, and zinc content, and I am varying aluminum percentage on my x-axis to see how the phase assemblage changes. All right, as you can see, there are different phases which appear in the system as you keep on increasing aluminum in the alloy. So this is one basic information that you can get. You can also calculate cooling paths here, all right? So this is a this is an equilibrium cooling calculation. So you're just cooling your alloy under equilibrium conditions, very slow cooling conditions. So on your x-axis you have your temperature, y-axis is your phase amount in log, and then you can see that you start with your liquid phase. This is your Liquidus temperature, and then you have your HCP phase which is formed first, and then there are different phases that precipitate in the system as you decrease the temperature. All right, so this is a very simple equilibrium calculation, and this is your enthalpy calculation for a compound, all right? So this is for an alloy, in fact. So this is your magnesium aluminum binary alloy. You can calculate your heat content of the system. So this is very important for the people who are doing CFD calculations, right? So in order to solve your temperature equations, you need your enthalpy content as a function of temperature, right? So these are some of the calculations that you can do with Faxage. And then this is very interesting. I have one case study with this as well. So this is your density calculation or molar volume calculation with your temperature for is a 3-1 alloy. So this is 3 aluminum, zinc, manganese. You can calculate the variation in your molar volume as you are cooling the alloy. All right. So this is very important for casting people, right? I mean, we need to know the change in the density when there is liquid to solid transformation, which is solidification, right? And that gives you an idea on how you control your porosities and other solidification defects. All right, so you might want to have an idea on how much percentage your density changes during solidification, right? So these kind of molar volume calculations help you to understand the change in your density during solidification. So this is also something that you can do. And then, all right, so this is one more phase diagram example for aluminum, iron, silicon alloys. So this is aluminum, iron, magnesium, silicon. So this is what we call a Liquidus projection in a binary frame. All right, so this is a Liquidus projection. Does everyone know what a Liquidus projection is? A ternary Liquidus projection. So Liquidus projection is nothing but you tend to cool your liquid. I mean, you are just trying to project the path of the change in your composition of liquid with temperature and composition. That's a Liquidus projection. All right.
So how the iron is taking part in this problem?
Yeah, let me finish. So you can see you have aluminum, iron, magnesium, silicon phase that appears here. So without iron, there is no aluminum, iron, magnesium, silicon phase, which is, now this phase is a kind of an impurity, right? So with 0.358% iron, you can see that you have this alpha aluminum iron silicon phase that comes in your system. So a little bit of information on how you interpret these diagrams, right? So on my y-axis is silicon, x-axis is magnesium, all right? So these are your temperature contours, okay? And this is your primary crystallization region for Mg2Si. So what it means is if I fix my composition here, if I cool my liquid, Mg2Si would be the first phase to appear in the system, okay? So this is the information, this is how you interpret the information in a liquidus projection, all right? So this is your primary crystallization region for Mg2Si. Similarly, this is the primary crystallization region for silicon, and this is your aluminum region, right? And 556 is your ternary invariant point, okay? So now if you don't have iron, of course you do not have any iron containing phase, and the idea is that when you add 0.358% carbon, you clearly see a precipitation region for aluminum, iron, magnesium, silicon phase. All right, so this is some of the, and of course you want to avoid this composition region, right? Because you don't want this phase to form during your casting, right? Because you are putting iron as this phase is an impurity. So this is some information. So recently, so this was more related to some calculations, but please remember you are still doing equilibrium calculations, right? And the process that naturally occur could be far from equilibrium conditions, all right? So we can also incorporate some non-equilibrium processes. We can incorporate, for instance, the effect of cooling rate during solidification. We can incorporate the effect of length scale. Like, I mean, you can calculate what is your secondary arm spacing, what is your primary arm spacing during solidification. You can also calculate whether the microstructure would be columnar, equiaxed, or mixed. Things such as transition, cellular to dendritic transition, columnar to equiax transition. So all this information can be known as well. So after solidification, you can do some more homogenization calculations. This is with temperature and time as well, because with time you tend to homogenize your sample, your secondary phases tend to dissolve. So these kinetics can be taken care as well. And then of course you can do precipitation calculations, or if you want to simulate your aging process, for instance, what is the aging kinetics in your alloy, what is the change in your precipitate size, precipitate volume fraction with time, all these calculations can be done as well. All right, so this is on top of FACSage, all right. So currently at this version, we cannot do these kind of calculations, but in July, from July onwards, we'll be able to incorporate kinetics as well. All right, so this is very useful for people who are doing alloy development and things like that. I'll quickly go through a couple of slides. So solidification model is extremely useful. So what we do is we try to predict the effect of back diffusion. You can calculate the segregation in your microstructure, right? People who are in casting and alloy development, segregation is something that they would really like to know. So you can calculate your segregation with respect to your cooling rate and composition. You can also calculate the secondary phases in your microstructure, right? So this is something that people really want to calculate before they step into homogenization cycles, is that what are the different amount and chemistry of the phases that are there in your as-cast microstructure. So this is also well known. You can calculate your arm spacings and things like that. Homogenization, it's so what basically we are solving Fick's law. So this is your multi-component Fick's law. So here what you do is we take the output from the solidification model. So in homogenization, what happens is you tend to remove the segregation, right? I mean, with time and temperature, the segregation is reduced, all right? So these are the kinetics that you calculate in homogenization, and in addition, your phases, your secondary phases also dissolve in homogenization, right? So these are some of the kinetics that can be taken care in this kind of a calculation as well. And then of course the precipitation, we can, as I said, we can calculate the evolution of different precipitates, of the size evolution of precipitate, the volume fraction of the precipitate, the number density. So all these kind of important kinetic information could be calculated from the precipitation as well. So these are some of the functionalities of Faxage that we can do currently. And now let me show you some quick examples here. So what I have plotted here is the total segregation, all right? So this is the total amount of secondary phases in your microstructure after casting, all right? So this is what I mean by total segregation, and this is x-axis is your cooling rate. So of course your segregation would change with cooling rate, right? And so I have compared my calculations with some of the experimental data for some aluminum alloys. So here, for instance, this is aluminum copper magnesium, and this is aluminum copper magnesium silicon. So these are the predictions or the calculations from the solidification model, and as you can see, the model can predict the segregation after as cast microstructure very well. So this is some of the preliminary results for the precipitation. So this is your aluminum scandium alloy. This is the change of size of aluminum 3 scandium. So this is your precipitation hardenable phase in aluminum scandium alloy. So as you can see, the change in the radius or change in the size of aluminum scandium with time at I think it was at 120 degrees. So this is well predicted as well. And this is again Mg2Si precipitate change in size with respect to time here. So this is a very important precipitation hardenable phase that we are interested in, especially in 6000 series. And again more experimental data with respect to the particle density. So this is the change in the density or in the number density of your Mg2Si phase with respect to your aging time. So this is comparison of the model with experiments. So this is what I wanted to show you quickly of what kind of calculations that currently we are capable of doing. As I said, we can do any kind of phase diagram calculation. We can do very simple cooling calculations currently. For instance, shell cooling and equilibrium cooling. Does everyone know what shell cooling is? Have an idea what shell cooling is? So shell solidification is the simplest form of solidification calculation. It assumes that there is no back diffusion in solid phase and complete mixing in liquid phase. So that's one of the assumptions. It's one of the simplest model that is available in Faxage. But now we can also incorporate, so shell cooling does not incorporate the effect of cooling rate. So it's cooling rate independent. All right, so the segregation that shell model will predict would be independent of cooling rate. But now we can incorporate the effect of cooling rate as well. So, and then we can do all the homogenization calculations. We can do precipitation related calculations. The example were for primarily aluminum magnesium, but you can do any alloy that you are interested in. So the physics of the model would remain the same. All right, so case study 1, all right. So this was some alloy development work that we did. So here, this was we wanted to play around with the magnesium and silicon ratio. All right, so we were trying to design new 6000 series alloy. okay? And the idea was to play with magnesium silicon content and see the effect of adding chromium, okay? So the idea was to form aluminum chromium dispyroids in the system, all right, so that we can have good strengthening effects, okay? So we designed a couple of alloys. So alloy 1, as you see, is without chromium. Then you have 0.28% chromium. Alloy 2, again, you have different magnesium to silicon ratio, and then you add 0.2% chromium. So we want to see what changes in terms of microstructure development by changing magnesium to silicon ratio and by adding chromium, all right? And one of the questions was how to choose homogenization and your rough extrusion temperature by doing some calculations, all right? So this was the final aim, that change magnesium to silicon ratio and choose a proper homogenization and extrusion temperature for each of the alloys, all right? So this was the final aim. Okay, so this is very simple. So this is without chromium, this is your as cast. So this is your shell cooling calculations, all right? So this is, on your y-axis is your weight percent or your phase percentage, your phase amounts with temperature, and as you can see, we are, so this is your HCP phase, of course, and then you precipitate different aluminum manganese, aluminum copper magnesium silicon, different phases as you decrease your temperature, right? So this was your as cast. I mean, of course, you have to start from as cast and then we will homogenize it and then extrude it, all right? So it's important to understand what's actually happening during the casting, okay? So now let's see what happens when we add, okay, but before that, so okay, let me go there. Okay, so this is what happens when you add 0.2% chromium. So we were expecting to form some dispyroids, but it didn't, because all the chromium got dissolved in your FCC phase, all right? So it didn't form any chromium. So typically the profile remained pretty much the same, and let me, yeah, and then for equilibrium calculations, so this is your equilibrium calculation. So the other one was shell, okay? Shell and equilibrium are two opposite ends, so that they're two ends of the spectrum of the calculations, all right? So shell is roughly casting at, let's say, 40 Kelvin per second to 50 Kelvin per second, all right? So that's roughly the cooling rate that shell corresponds to, all right? And equilibrium cooling is extremely slow cooling, all right? It's somewhere around 1 to 2 Kelvin per second, all right? So doing shell and equilibrium calculation together would give you an overall idea of what's actually happening in real situation, all right? So you do calculation for one extreme condition, you do calculation for the other one, and then you try to compare both of them, all right? So that's the idea. So we do both shell and equilibrium calculations together. So I showed you shell, and this is your equilibrium calculation, and as you can see, your phase precipitation sequence slightly changes, all right? But the nature of the phases roughly remains the same. Okay, so this is some of the calculations that you can see, and let me just summarize all the calculations for you, all right? So 4 different alloys, we could find out, I mean, of course, the Liquidus temperature varies with your alloying content. Lowest T solution is the temperature at which you can perform your homogenization, all right? So this is, of course, without iron here. So for instance, okay, so the idea of to select the homogenization temperature is where you do not have any secondary phases, right? I mean, you just want to have single phase solution in your microstructure, all right, if possible, right? So that's the homogenization temperature that one wants to select ideally, all right? So this temperature range is would be your typical homogenization range, because in this temperature range here you only have FCC solution, okay? And if you go less than that, right, then you would have secondary phases in your microstructure. But this is very subjective. I mean, it really depends. If you want alpha phase in your microstructure during homogenization, you can select your homogenization temperature below this temperature as well. So this is the temperature at which your alpha phase starts to precipitate, right? So if you hold your alloy, if you homogenize your alloy below this, you can form some alpha phase as well. But ideally, that's not the condition. You would want to homogenize at a temperature where you have a single phase solid solution. So this is your typical temperature range, all right? So in this table, this is what it means, lowest T solution, all right? So this is the temperature that you can hold to form your single phase, right? This is very important information because you don't have to do a lot of hit and trial. I mean, you know, you have a clear idea that holding at this temperature can give you a single phase solution. Yes. Mm-hmm. Yeah. 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 Mm-hmm. Yeah. 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 So this is just the variation of the phases, weight percent of the phases with temperature, right? So AL, so for instance, if you're interested in aluminum chromium phase, so this starts to precipitate somewhere around 1320 or 1350. All right. So this is what I was telling you. Like, how do you choose your homogenization temperature, right? If you go below this temperature, you will have all the phases in your microstructure. And you want to choose your homogenization temperature. The idea of choosing a homogenization temperature is when you have a single phase solution. So this is your window where you can choose your homogenization temperature, right? And in the next slide, I have given lowest T solution. It means the lowest temperature at which you can hold your sample to, and if you go below that, you will have different secondary phases. You can have possibly different secondary phases. So this is some idea. Any questions on? Okay, and then you can also, I mean, if you are interested in high temperature aging, you would want to know the precipitate at 200 degrees Celsius, right? I mean, so with different alloys, the amount of total precipitates can also be calculated, right? And you can also know the nature of the precipitates as well at 200 degrees Celsius. I'm not sure if yeah. So for instance, here at 200 degrees Celsius, you would have Al2Cu phase in your microstructure, right? So theta phase, Al2Cu, you have aluminum manganese phase, and you would have aluminum chromium phase, and you have Mg2Si phase. So at 200 degrees Celsius, these are your phases: aluminum chromium, Mg2Si, aluminum manganese, Al2Cu, and silicon, right? Yes. No, this is just, it's, so just assume that the volume fraction is equal to the area fraction in this calculation.
That is not, that won't be equal to 1.
No, but so this is, yeah, so this is, this would be equal to 100%, right? I'm just showing you one part of the,
Okay.
yeah.
So that is relative.
That's relative, yeah. So it's percentage.
Okay.
Yeah, it's percentage. So this is percentage, not absolute, right? So this is just percentage.
And so what will happen at the point of intersection of two lines
Oh, this is just the phase transformation. So one phase is transforming to the other phase. So for instance, here, for instance, this at this temperature, you see that aluminum chromium silicon phase ceases to exist and it transforms to aluminum 13Cr2. This is what it means. Okay, but please remember this is equilibrium calculation, all right? You are holding it for a very long time, and this is what you typically do in homogenization. You hold it for a long time so that you dissolve all the phases from your as cast and you wish to achieve a single phase solution. How much time do you, yes? It really depends on the databases, all right? So the Gibbs energy function, so this is all based on your Gibbs energy minimization, right? So the sub-zero calculation really depends whether your Gibbs energy function is defined for sub-zero or not, right? And typically no. So we usually have 298.15 Kelvin as our reference temperature. So 25 degrees Celsius is the reference temperature. But that being said, if you have some data which typically is, which alloys are you interested in typically? Steel. So typically there is so you're doing some cryoprecipitation or something? Quenching and all. Yeah. So so that is different. I mean, if you're trying to do quenching calculations, that means you're just trying to preserve the high temperature phase, right? So that is okay. That for there you don't need any low temperature Gibbs energy function, right? But MS and MF temperature predictions are a little bit tricky. But the starting point of the calculations is still your Gibbs energy function. Yeah.
So another one is grade steel. So the precipitation phasing time with temperature.
Yeah. So that is.
On particular precipitation.
So what's your temperature typically?
560.
560. So yeah. So those kind of calculations that we can.
Sir, you have two things. One is when the homogenizing is done, one is precipitation. Then there is another solutionizing.
Yeah.
So what is the solutionizing also you calculate?
Yeah, we can calculate that as well. Yeah.
Okay.
Yeah, absolutely.
Yeah. We have to quench it.
You have to quench it. Yeah.
So we have to make some judgment regarding the solutionizing.
Absolutely. We can do that as well.
Because we have to make a correct before this temperature solutionizing is not.
Yes. I'll show you one example that we try to do it. Okay, so this is the idea. Yes. Yeah. So this is the summary of the calculations. So you can calculate your liquidus, solidus, lowest T solutions, the amount of precipitates, and other things like that. And you can choose your temperatures accordingly. So you can, if you wish to desire some phases in your microstructure, accordingly you can choose your temperature. And then it's the same calculation with iron, because it's very difficult to avoid iron in aluminum. So same repeated calculations with iron, and then I have said that it's impossible to get fully solutionized ingots because there was no temperature range for single phase solution. Alright, so you would always have thermally stable precipitates in your microstructure if you have iron in your alloy. So this is one thing, and then yes. So this is typically the summary. So this was a real alloy that we got. For some reasons I cannot disclose the compositions, but you can make a guess of what the composition is going to be. But you can see that we started from as cast microstructure. So this is typically your as cast microstructure. 500.24 is where your solidification finishes. So this is your typically your eutectic temperature, and in your solidification microstructure you would have all these alloys. So other than your primary FCC, you will have alpha, theta, Mg2Si, Q phase, your silicon phase, and your aluminum, iron, magnesium, silicon, alpha and beta phase. Alright, so the idea in 6000 is that you choose a temperature so that you dissolve Al2Cu, Md and Mg2Si and then reprecipitate it during your aging. Alright, so we can take this as cast microstructure, and then we choose, so we repeated all those kind of calculations, all right, and then we selected 600 degrees Celsius as our homogenization temperature, all right. So when you homogenize it at 600 degrees Celsius, you see that all the phases would dissolve except your alpha phase, which is your thermally stable precipitate, all right. So all the other phases, copper, silicon, your Q phase, they all dissolve back in your aluminum matrix. All right, so you have a super saturated aluminum matrix now, and then you have, along with your super saturated aluminum, you have your alpha phase as well. All right, so now this is a very qualitative calculation here, that what happens if you extrude this at 400 degrees Celsius. All right, so what we do, we take this aluminum out of the calculations. So basically this is the phase that is being extruded primarily, and then we can do a quick equilibrium calculation at 400 degrees Celsius. The idea is, what are the phases that can precipitate during extrusion? Okay, so this is a very qualitative calculations, and then it tells us that at 400 degrees Celsius, if you do extrusion, you would have alpha phase, of course, and then you can precipitate your aluminum iron 5 phase, some chromium phase, and some Mg2Si phase as well. So this is some qualitative calculations at what can happen if you try to extrude this at 400 degrees Celsius, all right. So this is some of the calculations that we did. So we suggested these temperatures, they did the, they followed this this cycle. We suggested some time as well. They followed this, and it eventually developed into some kind of an alloy which could be commercialized. So this is some of the work, and then, I mean, of course, this is some sort of an empirical relationship, that if you have to know the ductility and strength of your alloy, depending on your precipitate size and amounts, you can do a very qualitative calculation. So what I'm trying to say here is that your ductility and strength after extrusion, you can form some empirical relations also and calculate the strength and the ductility of your alloys as well. So this is something that we did as well. Yeah. So case study 2. So this case study was related to aluminum 6061 as well, and they wanted to select the homogenization temperature. They were having some problems. So some company had some problems in selecting the right homogenization temperature for this alloy. All right, and then of course in some later processing stages, they were having some problems related to extrusion. So they thought it's some problem related to the selection of your right homogenization temperature. So they wanted to know what could be their homogenization window for this alloy and the phases that are appearing. So this is your typical composition, and this alloy had some titanium as well, and base composition is your 6061, and then you have some chromium in it as well. So this is the as-cast microstructure. The phases were typically your Mg2Si, Al2Cu, and I have said aluminum, iron, silicon total phases, which includes both. Is anyone familiar with aluminum chemistry here? So I mean, you have alpha and beta. So this is your total alpha and beta, and then you have some tau phase, aluminum, copper, zinc phase as well. So this is your typical as-cast microstructure, and then when we did the homogenization temperature, we all different phases that appear. So you have zirconium, titanium. I mean, this is a zirconium-like phase. No, you do not necessarily have to have zirconium. This is related to the crystal structure. Mg2Si, and so this is basically titanium, silicon, Si2Ti, Mg2Si, and you have aluminum, iron, silicon beta phase as well. So depending on your temperature, you could have different phases. So I selected two different extremes, and I wanted to show you the different phases that appear at 500 and 600 degrees Celsius homogenization. So at 600, you obviously see that you start up seeing liquid phase. So 600 is one extreme. You cannot homogenize at 600 because you will have incipient melting, and this is not really cool. So at other end 500, you see that you still have some Mg2Si, Si2Ti phase, aluminum, iron, manganese, silicon, alpha phase, and then titanium, aluminum, silicon phase. So these are some of the phases at 500 degrees Celsius. So we did calculations between 500 and 580, and so these are some of the microstructures. Okay, so these are your microstructures at 540 different times, 555 and 570, and you can see that all the phases are not dissolving, right? I mean, there are definitely some thermally stable precipitates here. So even after 24 hours of your homogenization, you're not getting a single phase aluminum, right? So the idea is what's happening in this microstructure, and clearly you could see that the area fraction is definitely reducing, right? So from 1 hour or from the as-cast all the way up to 24 hours, you could see that at least some area fraction is decreasing, but in a given in a broader scenario, you see that it's pretty much remains constant. So there is no change in the microstructure except for a slight decrease in your volume fraction. All right, so this is something very interesting to interpret, and
Normally 8-hour working is okay for the industry. 570 is the ideal temperature for 8 hours.
yeah. So but we selected 580 and it worked. But they were also interested to know that what are the phases that are actually dissolved. So the idea is whether your Al2Cu and Mg2Si are dissolving back or not, right? And what are these different phases, iron bearing phases? And so this could create problem during extrusion. So they wanted to modify the morphology as well. So this is some results, and so they also so this is a very qualitative estimation of your change in your area fraction of your secondary phases with homogenizing time at different temperatures. So as you can see, your area fraction is decreasing, and with the calculations you can see that it's Mg2Si and Al2Cu which are dissolving, and your aluminum, so titanium, aluminum, silicon phase. So your titanium, aluminum, silicon phase, your iron containing alpha phase, and your titanium, silicon phase are your thermally stable precipitates. So they don't dissolve even after you hold them for a very long time. All right, so this is something that they wanted to know, and of course in the later processing stages they want to change the morphology of this phase, because this is very detrimental for further processing. So once they confirm that yes, this is your iron containing alpha phase, they want to work around with it. So this is one of the ideas. Okay, so let me go through this case study. Yes, so this is about your porosity and your solidification shrinkage estimation. So we all know that aluminum silicon alloys are very prone to shrinkage during solidification up to a fixed addition of silicon. So after 4 to 5-8% silicon addition, you start seeing an improvement in casting. All right, so you start seeing a reduction in your porosities, your shrinkage is minimized as you increase your silicon content more than 4 to 5% in your alloy. All right, so this is the calculation of your molar volume with different temperature. Okay, and this is, as you can see, this is for pure aluminum. You see so this is your liquid. You have pure aluminum solidification, solid phase, and you can see there is a change in your molar volume. All right, it might not look a lot, but this can produce a lot of problems in casting. Okay, so this is, and as you can see, when you keep on adding silicon, all right, so the change in your molar volume in your solidification or your mushy zone between your liquidus and your solidus. So this is your liquidus and this is your solidus, right? So the change in molar volume between your liquidus and solidus temperature is getting minimized or is getting decreased. All right, so with some experimental, so people have done a lot of experiments in the system. You can derive a very qualitative relationship that if you have a certain X amount of volume change, it is associated with Y amount of shrinkage, and then you can work around with that empirical relationship in minimizing your porosity or your casting shrinkages. All right, so this calculation kind of supports that why do you see improvement in casting of aluminum silicon alloys when you have silicon around 5% or more than 4% in your alloy. All right, and this is these calculations are possible because of the volumetric databases in the system. So you have a Gibbs energy databases and then you have volume containing databases also. So you can calculate molar volumes as well, which are useful in this kind of calculations. Okay, so this is semi-solid case study 4. Let me come back to this. Let me show you case study 5. So this is 7050 alloy, very popular aerospace alloy, but it does have some problem, and the problem is associated with the S phase. All right, so S phase has been a headache for aluminum community for a very long time. The problem with this phase is that it reduces your fatigue resistance. All right, so this phase is responsible for your fatigue, for your reduction of fatigue resistance. So the community always wanted to minimize the S phase in the microstructure. All right, so there are some ideas on how to do it. Okay, so the idea is, the overall picture or the overall aim is to reduce the S phase in your microstructure, starting from upstream side, starting from your solidification side to all the way up to homogenization side. All right, so just to give you an idea, so this is the base composition: copper, magnesium, silicon, and then so this is a rough shell cooling calculations, a very basic solidification calculation. And if I zoom this portion up, you can see that I have now this is fraction out of 1. Okay, so I have some S phase in my microstructure at the end of the solidification around 740 Kelvin. So this is Kelvin, not Celsius. So what do we do about it? We know that from the upstream side we have S phase, and this phase, the chemistry of this phase is aluminum, copper, magnesium. And then the question is, what do we do about it? How can we get rid of this phase from the upstream side, or is it possible to minimize it, if not completely getting rid of it? So one thing that we could see clearly is the effect of the cooling rate. Okay, so this is done using the solidification software that I showed you earlier. So this is not shell cooling. So this is real calculation. So this calculation incorporates the effect of cooling rate, intercooling, back diffusion. So all the kinetics that happen during solidification is encountered in this calculation. So on the y-axis is your second phase fraction, all right, and this is with cooling rate. And I have also superimposed the shell cooling. So this is the total second phase fraction, and S phase is a part of it. Okay, and as you can see, shell cooling is constant because, as I said earlier, it's independent of the cooling rate. It's a very basic calculation. There is no effect of cooling rate. And one thing that these calculations tell us is that of course, I mean, shell cooling kind of over predicts your segregation, right? So this is very obvious here. And then it also says that if you cool it very quickly, around 1000 Kelvin per second or more than that, you can reduce your segregation. All right, so this is one, I would say something like an academic study. I mean, industry is definitely not going to be happy with it because they don't want to change their casting. Yeah, yeah. So yeah. Yeah, you can do melt spinning ribbon. So there are some rapid solidification techniques that. Yeah, it is possible, but not in industrial scale. I mean, so here, I mean, typically 7000 they do it typical ingot casting, right? So they are somewhere around this range, 10 to 50. So 10 to 50 Kelvin per second is where the actual real casting range is. But we wanted to show that, I mean, if you really want to make some alloys where you can minimize your S phase, is that you go higher. If you can solidify at a rapid or at a very high cooling rate, yes, you can decrease your second phase fraction, but this is not very good idea. Then we were left with one more idea that we started to work upon is change your magnesium to zinc ratio in the microstructure, in your alloy, sorry. So if you can play around with magnesium to zinc ratio, you can also minimize, yes. Because this selection was based on some of the strengthening calculations that we did at the end of your homogenization. See, you want zinc in your FCC structure, right? And you also want MgZn2 as your final strength. So MgZn2 or your lavas phase is your precipitation hardenable phase. All right. So if you are trying to play with the ratio, you might end up having less MgZn2 during precipitation or during aging, right? But you can also have that zinc back in your FCC. So it's solid solution strengthening versus your precipitation hardening. So we did a lot of calculations, your strength predicting calculations at the end of aging and end of your homogenization, and we found out that magnesium to zinc is the best combination to vary and have the same strength levels. So do not lose on strength, but minimize the S phase. So that's the overall idea. So this is what we did, and one of the interests. So we modified the S phase here. So this is your typical equilibrium calculation. So one of the things that we noticed again is that S phase can re-precipitate, right? So this was one more headache. That yes, I mean we could somehow minimize it by modifying the composition during the casting side, but then we ran into the problems that it can also reprecipitate. So this is your kind of a, I don't know what color is this. So this line is your S phase here. So as you can see, if you homogenize it, it is going to reprecipitate. All right, but we had no option. This is inevitable. This is going to happen. So, but one of the things that so this is the final picture. If you are interested, we published this work. I can share it with you. So this is the final picture. So this is your equilibrium S phase at 700 Kelvin. So this is your phase that could appear in your microstructure at if you homogenize it at 700 Kelvin. But when you modify the composition, right, and you can considerably decrease your S phase fraction. Okay, so this is your modified AL705 7750 alloy, and this is your line, and then this is the cooling calculation. All right, so this is 7050 which I showed you earlier. So this is just the S phase fraction with cooling rate, and this is the modified S phase fraction with cooling rate. So in modified aluminum 750, I could reduce the S phase during the casting as well. So I can considerably reduce the S phase during the casting, and during homogenization, I could also reduce it as well compared to the baseline 7050 alloy. So this kind of an idea actually worked, but we still have to evaluate other downstream properties which we are currently doing right now. But this kind of calculation was encouraging. Okay, so this is one of the last case studies. Then we can take a break, and then I can, if you have any calculation related to this kind of case studies that I showed you, we can do it here. We can do it runtime, and hopefully it can be of some use. So this is related to recycling of aluminum alloys, and as you can say, one of the problems during recycling is your iron, right? Because iron is an impurity from the casting side, and then the idea is how do you minimize the iron impurity during the casting itself, right? So one of the solution is to add manganese. Okay, so this is the phase diagram for aluminum silicon iron with manganese content here, and of course this is your temperature, and so typically around typically this aluminum iron silicon beta phase. So this contains, depending on your temperature, around 10 to 15% carbon, 10 to 15% iron. So this phase is what dissolves all the iron, right? So you don't want to precipitate this phase. Okay, so the idea is to move towards aluminum iron manganese silic alpha phase. So here it does have iron, but the solubility is less than 0.1%. All right, so the iron is considerably less here. So the idea is that you need to be somewhere around this composition region. So somewhere around 3% manganese, somewhere around like 2.5 to 3% manganese, then all your iron goes into your liquid phase, okay, which is good thing, rather than precipitating as your silicon, because you are eating up silicon also, right? You are taking up a lot of aluminum also with it. So rather than precipitating with beta, try to have this alpha phase and let iron go in liquid aluminum or liquid phase. So this kind of phase diagram gives you an operating window that, okay, what would be your temperature and what would be your rough manganese content that you need to add so that you can remove your iron. So this is, it's the same kind of a calculation. On my y-axis, I have weight % of species inside liquid phase. Okay, so this is iron and manganese inside liquid phase, and this is manganese percentage. I have fixed my temperature now, right? I could fix my temperature, and you could see that at 620 degrees Celsius with manganese addition, right, my iron phase is coming down here. I can remove my iron and my manganese increases, and then so this is, of course, now I can fix, so now I can select 3% manganese here. So now this is 3% manganese, and then this is with temperature, and as you can see, as you decrease the temperature, you can remove more iron from your liquid phase. So low temperature around 550 and 3% manganese is ideal for your iron removal. So kind of a recycling calculation if you want to see it as. So this kind of calculation, yeah, so this is kind of calculation that I did for deciding the operating temperature and your manganese concentration, so that you can remove iron during recycling. So this is kind of an idea. So this is this kind of concludes my presentation on the different case studies. I did not know that there are people who are interested in steel and titanium. For some reason, I thought this is mostly aluminum. So everything was based on aluminum, but we can do calculations now if you are interested with the alloys that you are interested in. And yes, thank you very much for your time, for your patience, and maybe 5 to 10 minutes break, and then we can you can jot down your problems, your alloy composition, and then we can take one by one the kind of calculations that you are interested in. Okay, thank you. Titanium, okay. Uh-huh. I'll just drink some water. Okay, so this is the software, and so typically if you want to have an idea of what databases that you should select for your calculation, then this is the window. So for instance, as I showed you, FT Lite. So this is your FT Lite database. It contains all the information that you want. So this is FT light. You can so it tells you what are the composition ranges, what are the systems that are done, what are the different solution phases. So it has around 210 phases or something. So for instance, in order to get accurate calculations, you need to select the right database, right? So the calculation that the lady requested is 45 aluminum, 5 niobium, 0.2 boron and 0.2 carbon. So this is atom percent, right? So here the idea is that the accuracy of the calculations really depends on how well the system is present in your database, right? So this is 1, 2, 3, 4, 5. So it's 5 element system. So it has 5 C2 binaries, right? So 5 C2 binary. So 5 C2 binary combinations and 5 C3 ternary combinations, right? So if all the combinations are done properly and the database is made and constructed properly, it will give you good results, right? The other way, what happens if the database is not present, what the software does is you need to check in the software whether how good are your binaries done, right? So as I said, the binaries are your 5C2. So your first binary is titanium aluminum, titanium niobium, titanium boron, titanium carbon, and then aluminum niobium, aluminum boron, aluminum carbon. So these are your different binary combinations. Even if your binary combinations are done well, it extrapolates into multi-component systems. So there are some mathematical functions in which the binary interactions are extrapolated to ternary interactions, all right? So at least if the binary is there, it is a reasonable calculation. But if your binaries are not present, then it would be an incorrect calculation or not correct or not a very accurate calculation. Because if the binary interactions are not there, it's just going to assume an ideal solution. All right, so it's going to assume that everything is ideal, there is no intermetallic, there is no solution. Okay, so the first thing you have to do, you have to check whether your binary interactions are there or not. Okay, the other thing is, in FactSage we do not have a dedicated titanium database. Okay, for instance, Thermocalc has a dedicated. Has anyone used Thermocalc's titanium database? Yeah, titanium database. So that is dedicated entirely to titanium calculations. Okay. So for instance, we have, for instance, fertilizer. I don't know why do we have this, but for instance, we have this salt databases. Okay. So this is related to all the halide system, NaCl, KCl, MgCl. So for instance, this is a very important system for aluminum production, right? So these salts are used in your electrochemical reduction. So in order to optimize that, we build this database, all right? So every database has a purpose. So light alloy database typically is for aluminum and magnesium. Okay, steel database here, where is it? Yeah, so this is for steel. Okay, for all kind of steel calculations, this is done. And then for slag calculations, you have FT oxide database. So it should be somewhere here, FT oxide maybe down in the list. And then you have for copper calculation, for copper alloys, you have copper alloy databases. So the point is, we do not have accurate titanium database like Thermocalc, but we can still give it a try from the binary extrapolations. Okay, so the first thing I'm going to check is whether we have titanium aluminum or not, and I think we should have titanium aluminum, but still. So this is what I typically do when I get a new system. So yes, aluminum titanium interactions are there, and then I'm going to check. So I can select either of these databases, right? I can select SGTE or FS steel or anything. The next thing I'm going to check is titanium niobium. And yes, so niobium titanium is also there, and then titanium boron. So I'm checking the interactions of titanium with all the solutes that you have given me, right? Even if that is sufficient, it will be okay. So titanium boron, yes, so titanium boron is also there, and then titanium carbon, of course, should be there. Okay, so I'm going to select the SGTE database for the calculations. Okay, so this database has most of the interactions, I believe, and let me check some other combinations. So aluminum niobium, for instance. Yeah, so aluminum niobium is also there, and then I'm going to check aluminum boron. Yes, aluminum boron is also there. So the reason I have to do this is because I do not have a dedicated titanium database. If this was an aluminum or a steel calculation, I would blindly do this in FactSage. But since this is titanium, we do not have the database, so I have to find out where are the interactions, most of the interactions. Yes. As I said, if you are really looking for accurate calculations, very accurate calculations, you should have all the binary interactions. So binary, so what is 5C2? So I don't know what that number would be. So these are, all the binary interactions should be there in the database. And if you have to go a step further, you should have the interactions for the ternary also. Okay, so 5C3 combinations now. Generally after ternary, we do not expect much interactions in the system. So the more solutes you have, the interactions are minimized. Okay, so generally binary to ternary are enough. Okay, so that's why I'm checking one by one. But if I had a dedicated titanium database, I would not worry about it. Yeah, I would miss boron carbon and aluminum carbon interactions in the calculation. So for instance, the question that gentleman asking is, what if I do not have aluminum carbon? So let's say if aluminum carbon is forming aluminum carbide, I would not see it in my calculations, right? And if I miss boron or carbon, if any compound or solution is, if it exists between boron or carbon and I do not have it, I would miss it in my calculation. Okay, so this is what I mean by considering the interactions. You have a question? Yeah. So pretty much aluminum boron is there. Aluminum carbon is a very important system, so this should be there. Yes, so it is there. So boron carbon, for instance, I think it is not there, but I can still check. Oh no, it's there. Okay, so SGT 2014. Yeah, so this database consider most of the binary interactions. But for instance, if you want to see the ternary, let's say titanium aluminum niobium, for instance. Yeah, see, we do not have it. Okay, so we have titanium niobium carbon that is there, but I do not have titanium aluminum niobium. So what it implies is that titanium aluminum niobium, if I have a ternary compound, let's say, it won't be there in the calculations. If I have a ternary solution phase, it won't be present in the calculations. So if I draw a phase diagram for you right now, and I don't know if you have any experimental data or anything to validate it. So if there is any titanium aluminum niobium solution or a compound, it won't appear. So this is what I mean by accurate databases.
And you wanted any compound you want?
No. What I mean is, do you know if titanium aluminum niobium is there any ternary compound? Okay, so we do not have the ternary phase diagram. So that compound would be missing in the calculations. This is what I'm trying to say. Okay, so
We found the DI2 and no phase.
T-
That is missing here.
TI2 ALNB. Yeah. So that won't be present in the calculations. So this is, because of the ternary interactions are not there in the databases, so that won't be there in the calculation.
You can display that binary phase, isn't it?
Yeah, that binary phase would be. So titanium 2, so Ti3Al, those kind of phases would be displaced. All right? Yeah. So you want to vary niobium, right? So now I know that only the binary interactions are there. So you won't see aluminum, niobium, carbon, for instance.
So we keep titanium 44 as constant.
Okay.
Where is the niobium content? Like 5 niobium, 7.5 niobium, 10 niobium. We'll see.
All right. Okay, so this is where I enter the end members. So this is, and you want this in mole percent, right? Oh, this is mole. Yeah, so atom is mole percent, right? So titanium, aluminum, niobium, boron, and carbon, right? Okay, so these are my different solution phases that can form in the system, all right? So I'm going to select all the solution. So this is order disordered phase. I'm going to deselect it for the time being. So this is the order disordered phase in the BCC phase. And then, so these are the phases. So if you click phases, it says that the liquid solution, all right? So this liquid contains aluminum, boron, carbon, niobium, titanium. So what the software is doing that is, it has all the binary interactions and it will extrapolate it into this 5-component system on its own. So it would, so if there are any ternary interactions even in liquid phase, that is not considered. So it's just extrapolations from binary. Sometimes it's okay, sometimes it doesn't work, so you really need to know your system. So as the lady said, there is a ternary compound, aluminum, niobium, carbon. So we don't have this. So this might not show, and these are your compounds, your solids, pure compounds, and these are your solutions. So now y-axis will be my temperature. I'll vary it from 200 to, let's say, 2000, and now we can fix aluminum, right? So I'll fix aluminum, and this is constant, right? So this is 0.45, right? Yeah, and then next I will fix boron, okay? So this is 0.02. Now I'll fix my carbon, right? Carbon is, yeah, so 0.2, right? So this is out of 100. So out of 1 it will be 0.002. It's out of 1. It takes out of 1. And then I'll vary niobium, okay? So I'll vary niobium x-axis between 0 to 0.5. So 0 to 5%, okay? So let us check everything. So aluminum is 45%, boron is 0.2%, carbon is 0.2%.
So niobium can vary 5 to 10%.
Let's do this and see. And then okay, can take some time, of course. So while this calculation is running, what is the other, someone in steel? Yes, iron and, yeah, that should be very, so order disorder. Second, which phase? Yeah. So you want to see the phase stability?
Like if you plot an iron and aluminum binary phase diagram,
Yeah.
in thermocalc I don't see a line of Fe3Al.
Okay, we can check.
So can I see?
Good question. Fe3Al. So you can always go to the documentation while this calculation is running. I can see Fe. Yeah. Iron, aluminum. Let's see. Fe. So 3:1. So we have aluminum 13 Fe4. That is 3:1. This one. BCC. So, oh yeah. Okay, yeah. During the which simulation? Thermocalc. Yeah. Oh, this is the yeah. We are better than thermocalc, right? Yeah. yeah. I think which database are you using? I mean, yeah. Okay, so this is done. Okay, so this is the data. This is the phase diagram. So now I can label it. Okay, so let me just close this. So this is the phases that are present in this region. So titanium, aluminum, titanium FCC, BCC, and boron titanium, and I can go on labeling these phases. Okay, so these are my phases, and what I can also do is, if I want to know the phase fractions at a given composition of niobium, I can do that as well. So what I can do is I can click this bulb, I'll click this here, and then it says that at 1157 and this 0.0263 mole, let me see what are my phases. So it says that I have around 17% BCC, and these are my phase constituents inside BCC titanium. So I have niobium solubility, aluminum solubility, and almost zero boron and carbon solubilities. And then I have FCC, very little FCC, which is mostly titanium with carbon. And then I would have boron titanium and titanium aluminum also, which is given here. So I have around 0.41 moles of titanium aluminum and 1.9852 minus 3 moles of boron titanium. Okay, so this is yes, of course, I can save this one. So which region are you interested in? Is this enough, or do you?
Sir, I'm interested on from 5 to 10%.
Okay, so how about I give you 0 to 10% and then I'll save it.
Yes.
Okay. So let me close this. I can always plot this again. But I said, as I said, you have to be a little careful in the interpretation. Yeah, because
the volume fraction of the constituent fractions like your BCC, how
yeah.
can we save that part also?
So that is, we can do equilibrium calculation. So at each temperature, depending on your
No, upper India
Okay, okay. Let me just calculate this.
Yes, I have some EPJ results.
Probe results.
EPJ results I have.
Okay,
Then the EDS results I have.
okay.
This result I can confirm it. I can interpret.
From which temperature do you have? What
I
temperature?
have my temperature range is around. You are asking my aging temperature or solution with
Solutionizing. So which temperature did you quench your?
alpha plus beta phase.
Alpha plus beta phase field. Okay. So even, I mean, it's not going to end now. I mean, you can always send me an email, and
You may be busy and they will.
my students are always free, so they are sitting there. So they are very good in all doing all these calculations. So they know I'm never busy. I'm always free. So you can always so you can always send an email, and I absolutely. I mean, this is typically how we work. We want to validate the databases. Okay.
So I am setting some parameters.
Okay.
For gamma, like gamma delta.
Gamma titanium, yes.
So I want to find out that the processing window and everything I want to develop on this company.
Yes.
So I want to have this thermal diagram.
Yeah, yeah.
So I may require your help.
Absolutely. So just drop me an email whenever you need help, and typically I reply whenever I get an email. So if I'm not able to do the calculations, my students are very well trained, so they help me in doing all these calculations. So don't worry, I'm not someone who would not reply to the emails. Okay. Yes. So what other calculations can we take after this? Anyone? Anyone in? What's your composition? Steel. See, so usually I do a 3-day workshop for all this. So the first 2 days is usually software, and then third day is problems. But we have to do it in, you know, it's good that the camera is running. I'm one of the developers of the software. So you are asking one of the developers to give you a pirated. That's a bit strange, yes. Yeah. I'm sure you are working in a government organization, right? Yeah, yeah. So, yeah. Yes. 0.6%, yes. One second. Silicon is 0.1. Uh-huh. 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 Manganese is 0.95. Okay. Okay. Vanadium is 0.03. Okay. And aluminum is 0.04. Okay, let's forget the nitrogen right now. So what are you interested in? 0.04. Okay, so what are you interested in? 0.03. So what are you interested in this calculation? So what do you want? What's the information that you're looking for? Okay. Thermo processing, yes.
So I just wanted to know that my cooling temperature, cooling temperature,
Uh-huh.
cooling temperature.
Yeah.
At that time, what pressure?
So what is your typical range? Temperature range. Okay. 900 to 610, right? Okay. So what's your name again? So Rishabh, what I can do is, see, I can do a calculation, but this composition is very complex. It's going to take forever for the software to do it. So what I can do is, I think I can remove sulfur, phosphorus, okay, and remove aluminum, remove vanadium, and then just do a calculation with carbon, silicon, manganese, copper, right? And then we can do a more detailed calculation later, right? Or if you can, which organization are you from? IT Bombay. With whom? Oh, MVG and Prasad. Okay. Okay, good. Okay. So I'll save this. I'll label the phases. Yeah. Okay. So once you send me an email of your compositions and your solutionizing temperature and your aging temperature, and I can do or my students can do a very accurate calculation for you. All right, because see, here I have to do point by point calculation, which is a lot of data points. So that's not really useful. So once you send me a detailed email about your composition and your processing temperature, I can give you the calculation that what is the phase assemblage. Right. For the time being, I can give you this. All right. So the next is a steel calculation. So steel, I don't have to worry. So this is so he's interested in calculating your precipitates, the nature and the amount and the chemistry of the precipitates that might appear during the chemical treatment. All right, so he's using a Gibbs simulator to do that, right? Okay. So what I can do is I can do a equilibrium calculation for you, right? So you are interested the amount and the chemistry of your phases with temperature, right? So if I plot phase amount with temperature, that should be enough for you, right? Okay, good. Okay, so this is FS steel. So I have iron, carbon, silicon, aluminum, niobium, and copper, right? Manganese. So copper, so tell me in weight per, so copper was 0.6, 0.06. Silicon was 0.04, 0.1. Aluminum was, can't see it from here, can you just repeat it? 0.1 percentage, okay. Okay, 0.04. 0.5 manganese, and rest I'll assume everything to be iron. Okay, so you have around 98%, and then everything else is okay. So I'm going to select all phases. So these are your phases, and you said your temperature is, let's say I do between 950 to 650. Yeah, so I'm giving you. Select. Okay, and then so I'm going to plot results. Axis would be grams, temperature, and then I'm going to select all the phases that are formed. Okay. Yeah, so I mean, so 650 to 950. So I mean already. So you see that you only have FCC to BCC. So at your said at 600, see you said 650 or 610. Okay, I have to go lower. Sorry. Sorry. You might form some precipitates. So 900 to 600, right? Is that fine? It's fine, yeah. So output plot results, refresh, select all stable phases. Yeah. So typically, so you would see that you only have BCC and FCC phase in your microstructure, and if you want to see the, I don't know if you're interested in seeing the percentage of different phase constituents also, like in FCC, how does your carbon, silicon, and aluminum are changing. So these are your global phase amounts. So in microstructure, your microstructure is typically FCC, BCC in your temperature range. So is that it? So no, the calculations are not predicting any precipitates as such. I mean, it's just solutions. So this is just your austenite and ferrite. So it's not predicting any precipitates. No, it's not predicting any precipitate. So everything is soluble in your solutions. Yeah. So, but you have to be okay. So you have to be little careful. I see what you mean. So FCC phase in FACSage, so your austenite phase, so all your carbides and nitrites are part of your austenite phase. Okay. So if you see the results, for instance, at 650, for instance, or at 600. Okay. No, 600 is not. So for instance, at 650. Yeah. So 650 is primarily your ferrite matrix, right? And these are your constituents. So all your carbides are part of your ferrite phase. Okay. In your austenite phase, you see that you have two FCCs, FCC A1 and FCC A2, right? So in FACSage, what we do is we incorporate all the carbonitrites in austenite as well. So you have three phase miscibility. So you have austenite, you have carbides, and then you have nitrites, all three in one phase. Okay, so for instance, if you see in FCC A1, this is mostly niobium carbide. So you have to be very so FCC A1, this is your 0.5%, and out of this 98% is your niobium carbide. Okay, so if you're referring to precipitates, this is the precipitate that can form niobium carbide. Okay. Yes, you have to check both the data because it's the way we model the phases in software. No. In the, yeah, you have to check it individually. Okay, but so this is useful to do. Yes, I can give you the data. So what I'm trying to say is that yes, you do have niobium carbide precipitate, but it's shown as FCC. Okay, so this helps us to model easily, right? So you have niobium carbide, and then you have the other Okay, so this is also very interesting. So the other FCC phase is mostly composed of your copper, copper and manganese. Okay, so you can see you have, so this is a solution, austenite or austenite-like solution which has solubility of copper, iron and manganese. Okay, so niobium carbide and your copper-rich FCC phase. Okay, so 0.1 gram of FCC82, which is copper-rich, and then it has solubility of iron and manganese. No, it's vacancy. It's vacancy. No, it's not vanadium. It's vacancy. It's the way we model solutions. So one sublattice is all your. So this is the model. So this is two sublattice model. Are you aware with the solutions? So in one sublattice you have aluminum, copper, iron, manganese, niobium, silicon, copper, blah blah blah. And in the second sublattice you have carbon and vacancy, right? And then the intermixing happens between the two sublattices. Okay, so this is, the calculations are saying that you would have mostly copper soluble with iron and manganese in your at 600 degrees Celsius, and you would also have niobium carbide, and you also have your ferrite matrix. Okay, so this is 90. So this is BCC, which is 98% ferrite iron, right? And then it has solubility of manganese and other things. Okay, so you have to be a little careful in interpreting this result. Is this useful? Okay, so how do I give you this data? Let me, okay, what I can do is I'll save this for you and then I'll email you the data. Okay, I'll save this window for you so I remember, or drop me an email about this, all right? And so I'll save this. So your name was Bishop. So what are the phases that you see, Rishabh, during actual Global testing? Have you done it yet? Okay, okay. All right, so yeah, I can send you the data. So mostly you would be interested in your phases. So all the carbides and this kind of phase. Okay, and send me, so I have not included your vanadium and sulfur and phosphorus. So they can also form some precipitates, but we can do that later. Yes. All right, any more calculations of interest? Sorry? No, no. So no, you cannot calculate the ductility and strength, but there are a lot of empirical relations in literature which are dependent on your phase amounts. And so once you know your phase amounts, you can use those relationships to calculate your ductility and strength.
Can we find out the volume fraction?
So volume fraction, so this is what I mean. So so quenching is usually to preserve the phase assemblage at the temperature, right? And you hold it for a certain time so that you have the equilibrium phase assemblage, right? So if you can tell me at what time, at what temperature are you holding it, that are the same phases that you are going to see during after your quenching, right? So are you interested in, so what alloy are you looking at? Which, so what is your composition? Okay, I have to check. So we can do this similar calculation. So titanium zirconium, I think it should be. Yeah. So titanium, okay. Yeah, and let me check if I have niobium. Yeah, I have niobium zirconium as well. So as you can see, titanium, niobium, zirconium ternary interactions are not there. So is there any ternary compound in your system, or you're not aware of? Okay, so it's just going to extrapolate the binaries. Okay, so what's the temperature range that you are interested in? What temperatures are you quenching it from? Uh-huh. Okay. Okay. So at 900, it's saying that it should be mostly your BCC phase. Okay. So as you can see, at uh, at your it's mostly your BCC phase up to 700, and from your 700 your HCP phase starts. At 700 your HCP phase starts to precipitate. So at 900, as you can see, it's mostly your BCC titanium. So it's single phase. It's a single phase solution that you should have. See, uh, yeah, so it's an internal rearrangement of your BCC to BCT, right? So uh, that information it cannot provide you. That what is your MS and what is your MF? Those kind of calculations it cannot provide you. So you have to incorporate some kinetics into your calculations. Kinetics such as so for instance, quenching is okay, but you can also produce deformation induced martensite also, right? You can produce deformation induced martensite. You can then add the deformation energy to the Gibbs energy function, right? And then you can calculate indirectly that at what temperatures that your no, it won't. I mean, this is again thermodynamic calculations. So ternary diagram would give you the same information. It's just going to tell you that yes, you are quenching from BCC, your single phase, but at what temperature are you forming your that your martensite start temperature, or what is the volume fraction, or that information. You have to incorporate some kinetics. No software can do it for you, not even thermocalc. Yes, any other calculations? Yes. Uh-huh. Yeah.
So can we do like plotting a ternary diagram first and incorporating the data and then going on other calculations?
Yeah, so this is what we call the database development. And so if you do not have any data, or I mean if the database is not present, what we do is we develop the databases, right? So if you have any information for the ternary system, we can incorporate that in the existing database. So yes, that is possible, but that takes a lot of time, and you really need to have an in-depth knowledge of database development. Yeah.
Or even the same ternary plot that we plot,
Mm-hmm.
we get an experimental data file of that, like the phases in temperature or volume fraction,
Uh-huh.
the log file. So is there any possibility that we file and ask the software to calculate it.
To calculate what?
To calculate the further addition of another element to the text.
See, you have to understand, this is not how it works. You have to have a Gibbs energy function first, and then it will minimize it depending on your temperature, composition and pressure. Alright, so you have to have a Gibbs energy function, then only it can do the calculation. Otherwise, no, you cannot go backwards. Yeah, yeah. Alright, so any more? Yes. No, it's a alright, so alright, tell me the major ones. We can see. 1 second. 0.63, 0.063, manganese 0.89, silicon 0.26, and rest is niobium is? Yeah, this should be very accurate. Okay. So what temp? All right. So, this is, so if I zoom this up, for instance, so this is the phase assembly. So you have FCC, BCC. So if I zoom 0 to 10, increment at 2, label at 2. Yeah. So again, so as I said, so you have sigma phases, okay, and then you have carbides, and then you have FCC3. So yeah, so you have carbides. So let's look at the phases. So of course you have BCC, FCC, and carbide containing phases as well. So if I look at the phase analysis here, okay. So here similarly BCC. So right. So as I was explaining him earlier, that in FACSage we consider carbides, nitrides, and BCC or FCC in one single phase. So BCC also would have carbides and nitrides, and along with BCC iron. So that's why it has 3-phase miscibility. And similarly for FCC, we'll have FCC, carbides, and nitrides. So this is just for the convenience of calculations. So your calculation, so the calculations are indicating that around 400 you have around 81% BCC phase, which is your primarily iron. As you can see, this is vacancy, primarily iron, and around 10% chromium. Okay, so this is, and if you see, these are your system component. So these are your components inside the phase, inside BCC. So as you can see, this is around 86% iron, and then around 9.2% chromium. These are in the solid solution. So you have one BCC solution, which is primarily iron rich. As you can see, this is 86% iron. Yeah. 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 Yeah, yeah. Absolutely. So this is what we can check. So as you can see, niobium is not part of BCC here. So this is just here. This is just iron and chromium rich. And then I have BCC A2, which is carbides mostly. And this is also showing me that this is chromium rich. Okay. And then if I consider FCC, this is showing me that this is mostly iron and nickel with some solubility of manganese. And then I have FCCA2, which is around, it was similar case, around 97% copper. So this is copper rich FCC with some solubility of other compounds. And then, yes, so this is my niobium. So this is my FCCA3. So this is my niobium carbide, as you can see. Okay, so this is where your niobium is going in. So carbon is partitioned into different solid solutions, right? So carbon is partitioned primarily with let's check. No, it's not partitioned with BCC, but I think there are some carbides which are precipitating. Let's see. Let's check. Yes, so you can see there are carbides which precipitate around 400 degrees Celsius. Okay, so this is where carbon is mostly partitioned. Okay, you can see 100% carbon now. Okay, so why don't we plot carbon in all the phases? So if you have to, so your idea is to have carbon in niobium. So this is what you want. So if we plot carbon in different phases with temperature, then it will tell you where exactly it is partitioning with niobium carbide, right? And that is your temperature range. Yeah, everything should be in solution form. So when you say solution form, that is the second thing, and solution form is mostly your BCC, right? So FCC. So as you, yeah, FCC. Yeah, sorry. So as you increase the temperature, yeah. See, as you okay. So did I close this? Yeah. So as you increase the temperature, as you can see, so here at lower temperature you are precipitating all your niobium carbides and all other carbides. But as you go higher, you see that you have homogeneous FCC solution. Okay, so somewhere around 1050, you would just have FCC solution, one single phase. Somewhere around 1050. It's only single phase. No carbides, and we can check that also. So we can check that as well. Yeah, so around 1000, if you see, you have, or 1100, you have around 99.9 FCC. So, and you can see this is mostly your iron, and then everything is dissolved inside this solution, right? So all the carbon and everything is dissolved in this, and you have around 9.4 minus 2 gram of niobium carbide. So you would still see very little precipitation, but predominantly it's at around 100 degrees Celsius, 1100 degrees Celsius. Okay, so this is the correct. And if you go higher, 1200 is best. And if you go higher, I think you start precipitating your BCC phase again. So 1100 to 1200, I mean 1200 looks to be very optimum here. Any? So you mean the dissolution temperature? So yeah, I mean, so this is pretty much your dissolution. I mean, it gives you an idea of dissolution too, right? I mean, see, at 400 you do precipitate a lot of carbides, right? And so, but if you increase the temperature, you are increasing your volume fraction of FCC, so you're dissolving most of your carbides. Yeah. So these are some kind of calculations that, so it's saying somewhere between 1100 to 1200 would give you the best combination. So what is the current temperature, if I can ask you, that you are fixing? 1050. Yeah, so 1050 is, yeah, so at 1000 you have 99.8, yeah, so it's around 100%. Thank you. Yeah, absolutely. And if I'm not able to do all the calculations, please feel free to drop me an email. Any calculations, any help with any process. Oh, email me. I'll tell you. I'll get you a very good discount on my part. Okay, so this is. I'll just name it Bharat Forge. Okay. Okay, anything more? No pirated version, sorry. No, it's a combination of C++, Fortran, and Delphi. Yeah, are part of it, not everything. So the part of figure module I have done it, which looks awful, so I have to work on it. Yeah. So I guess if you do not have any more calculations, I can wrap this up.